Chelsea for coming tonight.
Thank you for having me. Thanks to both Lloyd and Journey. So hi, my name is Chelsea, and today I'm going to be talking about one of the biggest transitions you can make in your data architecture journey, which is how to partition existing tables. As a quick introduction to myself before I start, my name is Chelsea, and I work at a company called Brex as a software engineer on the data storage team. Previously to this, I was a data engineer, backend engineer. At Brex currently, we started as the credit card for startups, and then we sort of did a SaaS pivot, so now we're doing both. And within Brex, I work as a tech lead at the data storage team, which means I'm doing Postgres infrastructure, query optimization, all that fun jazz. Without further ado, let's get started. So the higher level of where I'm going to go with this talk today is to get to point 4 on here, how to partition an existing table. But in order to get to that place, we have to go through a couple steps and get into some context of what that means and why it may deserve an entire 45-minute talk. So I'm going to start out by learning what partitioning is, what it provides, doesn't provide, and how Postgres got to the place it is now over the course of its many versions. Then I'm going to go into partitioning in Postgres specifically, what types it provides, pros, cons of both, and how to think about partitioning and when you might partition or not. I'm going to go over some perceived benefits versus actual benefits, and then finally we'll make it over to partitioning an existing table. I'm going to go in this section through 4 separate migration methods, each of them with a different set of requirements and basically increasing complexity over the course of different options you may have and when they might suit your use cases. Finally, I'm going to finish off with some discussion of maintenance, configuration, and observability, what to do once you've gotten there. What is partitioning? Partitioning is the act of splitting a large logical table into n smaller physical tables. So here we can see that there is one logical table called students. On the left, we have a one-to-one mapping of a logical table, and on the physical disk mapping where it lives. If you partition that table, instead you're able to query students, but there's no actual data stored in the table space of students. Instead, when you query or insert to it or update or delete, it basically points to a certain table under the hood between 1 and n tables where the data really lives. In both of these examples, you can run a query like this. Select whatever from students where ID is 1. In both of these, you only need to actually query from the parent table. So the difference is sort of a physical difference. Where does the disk live for that table? You may have heard of sharding, which has a lot of similarities, but there are differences, which can basically be summed up to the fact that partitioning is an optimization of software, but sharding is an optimization of hardware. So when you shard a data set, you're splitting the data set across multiple nodes, multiple completely different servers. Sometimes people call this horizontal partitioning. But in this case, if I split students' table up into 3 nodes, then I'm basically 3xing the amount of CPU memory, except 3x the servers. And probably only a segment of the total data set is going to live on each of these. Whereas with partitioning, we're splitting one data set across multiple tables in the same node. This has advantages for software, maintenance, potentially performance that I'll get into later in the presentation, but it still has the same amount of CPU and physical resources. Partitioning in Postgres existed from, yield early days. PG 9.6 and before, partitioning was possible, but it was very DIY. You could do it yourself with table inheritance. So developers would manually create child tables, and when you insert onto our students table, for example, you would have to use a manually created trigger to figure out where that row should live. At this point, I would say, my personal assessment on the right, difficult setup, bad performance, not a fun time, high level. However, declarative partitioning, native partitioning in Postgres, was introduced in Postgres 10. And ever since then, it's basically gotten better version on version. On Postgres 10, they introduced native support of partition tables, meaning you could run create table students, partition by, etc., etc. And it also added native tuple routing and pruning for selects, which basically means that inserts know where to go, and selects can hopefully scan only the amount of data they actually need. At this point, Postgres is providing easy syntax, but very simplistic features. 11, it got a lot better. adding update tuple routing, partition-wise join, very critical usability features. And in 12 to 16, we've seen partitioning improvements, I believe, every major version, including attaching and detaching partitions concurrently, which is one of the major draws, partition pruning, improvements, logical replication on partition tables. And at this point, on Postgres 16 or 17, if you're cutting edge, we are now a mature first-class Postgres feature with partitioning. Partitioning methods in Postgres are range, list, and hash. The definition of what a partitioning method is essentially just how you define what data goes in which child table. So a partition key defines how an individual insert or select is mapped to where it's physically stored on those child tables. Range partitioning is, in my opinion, probably the most useful method of partitioning in my personal experience. It's also one of the most common. So in range partitioning, partitions will include values, the predefined min and max. So for example, in this partition we have integers 1 to 10 of a required column, and then the next one is 11 to 20, etc. Examples of where range partitioning is frequently used would be time range data, especially if you only want to query or mostly query the most recent data. Something like a dashboard of events could be supported by this, where you want to preload in chronological order. Maybe you see your expenses and you always load the first page. That might be easier. When you create a range partition table, your syntax would look like this: creating your table students with a bunch of columns. And you'll see that we have at the end partition by range of inserted at. Here, inserted at is the partition key, which you'll notice is a required non-nullable field. And then after that, I am able to create partitions. If I just ran the first statement and I tried to insert or delete from it, it would actually error. And the reason for this is that at this point, I've set up the parent table, but there's no place for the data to actually live. So it would actually error no matter what I tried to insert. So I have to actually manually create those partitions, create table partition of students with values from min to max as many times as I want. List partitioning is the second option you have in Postgres. And here, instead of being a min and a max, it's an explicit column value. So list partitioning is usually great when you have a low cardinality field. So for example, maybe I have data that's separated by user region, and I always want to query for US or maybe APAC or anywhere else. Maybe I want to bulk load or drop by list partition, because another feature of partitioning is I'm able to sort of add and remove full partitions at a time without running into some of the long locks and MVCC constraints I would see in a regular table. With list partitioning, in general, you want to go for it if your potential values for the primary key don't change dynamically. So for example, with EU and APAC, that's a great example because, unless Atlantis pops out of nowhere, there's kind of no room to grow there. I don't have other regions I need to be introducing. And because if I needed to introduce a new region, that would be a migration probably in however I manage my migrations. Whereas if I was list partitioning by first name, that'd be a very bad example, because every time somebody with a new first name entered the site, it would probably error until I was able to add the migration. If I was going to create a list partition table, looks basically the same. In this case, I'm going to list partition by grad year, which is going to be a required integer. Then I'm doing the same thing, adding a partition for values in 2013 and 14. But then you'll see there's a new fourth line at the bottom, which is create table partition of students default. So now I said that if you create the parent table and you don't add child tables, it'll error. Well, this sort of is a catch-all for that. This prevents a bit of a foot gun situation where you can accidentally, run yourself into a bad place by not having a valid list partition available. So if you create a default partition, let's say I try to add a value with a grad year of 2025, there's no explicit partition, but it would go to default. And I'll mention some of the potential anti-patterns with that later on. Hash partitioning is the third and final built-in way. Hash partitioning, I would say at a high level, TLDR, use it if you really need to use partitioning. There's just no other way. It just got to happen for maintenance reasons, but there's no obvious partition key. There's no obvious, really consistent way you're reading or writing to this data that might add some logic to partitioning. In hash partitioning, you partition based on the hash value of a column or even multiple columns at once when you define the modulus and the remainder. So usually, you just want to distribute these values naturally. An example of how you might do this would be, in this case, again, students, partitioning by hash of ID. And here I'm going to say from the beginning, I'm setting modulus 3, so I know I'm going to create 3 partitions. One difference between hash and any other type of partitioning is that in hash partitioning, once you create the table, you are really locked into your partition count. Because I've decided modulus is 3, if I decide later on that I want to actually create more partitions, maybe they grow to huge size and now each of these is an enormous partition all on its own, you're kind of out of luck. You have to completely restart the partition migration process again. And the reason here is sort of a bit like, you can think about it logically. If you were to try to add a fourth one, modulus 3 or remainder 3, you would break the logic with which Postgres is actually deciding where your tuples live or are read from. So you're locked into this, unlike the others. It also means that it doesn't have the same attach, detach feature or kind of value that you might get from other types, because there's no logical value in attaching and detaching hash partitions. So going through all this, you might wonder, why partition? Why partition? What does it actually bring? So partitioning has some direct guaranteed impact that you're definitely going to get. Check the box, no ifs, ands, or buts. And these direct guarantees can, in some circumstances, lead to potential downstream impact as well. So the guaranteed impact that you would see includes faster parallelizable auto-vacuum. The reason you would get this is because from Postgres' perspective, partition tables are just tables. I sometimes myself think of partitioning as like a user experience thing for Postgres DBAs, because you as a user see one table with different places the tuples live, but Postgres, it just sees a bunch of tables. So Postgres is going to be able to run auto-vacuum and a more faster parallelizable way, because it can be auto-vacuuming smaller tables at once. Same thing goes for index maintenance. When you partition a table, let's say I have 5 partitions under the hood, I have, instead of one big index, I have 5 smaller indexes. So maintenance can also be parallelized, or it can also be made simpler. You're not holding these long locks that might be problematic to the system. One kind of nice to have that's a bit of a one people don't think about is with range partitioning, you get some what I think of as bucketed natural page ordering. The reason for this is because, again, if I have range of, let's say, 1 to 10, 11 to 20, etc., each of those, 1 to 10, is going to be its own table space. And each of those will be inserted, tuples will be inserted to it at random. And Postgres doesn't insert in a logically consistent way. It's whatever it has room for. But because you've made it a smaller range, it's more likely that you're probably going to be able to read from it in a more logically consistent way, versus if you had one table that was, say, 1 to 1,000. Also, safe and easy bulk data deletion and creation with attach and detach. So if I create my APAC, my students in different regions, and I do want to, let's say, attach a whole new region, then what I can do is I can create that table separately, fill it with data, and then instead of running, a maybe many hours or days long backfill where I'm programmatically inserting them, and then, maybe I'm running into issues with bloat if I need to do a bulk delete and all this other stuff that's kind of caused by all the nice things Postgres gives us with MVCC. Instead, I can just run an attach or detach, and it'll add it all at once, instantly, without all that overhead. The indirect probable impact that I would say that you shouldn't promise to anybody who's telling you to partition, but might happen, is things such as query performance improvements, bloat reduction, and better cache efficiency. To kind of dig into why we might see these advantages, but only might, you can kind of look into each of these sections. So I said we have faster parallelizable vacuum because we have many small tables instead of one big table. In this case, we have a more recent X-min horizon from vacuuming more frequently, from it being shorter. This, in turn, will lead to less bloat, potentially bettering your query performance because you have less I/O for your scans. You also will keep the visibility map up to date, which helps you to perform fewer heap fetches. With faster index maintenance, I would say overall, this kind of goes to show for itself, faster index maintenance and faster maintenance in general is just a good thing, but also building and rebuilding is lower impact, more recent X-Men horizon, and just human-wise, you probably just do it more often if it's low impact to your system compared to, okay, I have to schedule Saturday at 2 p.m. to do this index rebuild. You'll probably just be able to do it more often on your team, keeping your database in better health. Natural page ordering will also freshen your data in shared buffers, helping query performance, and potentially having better cache efficiency. And finally, again, as I said before, the bulk, delete, and insert without table bloat or resource usage can lead to fewer locks, but also smaller, potentially cheaper disk, depending on how you're paying for disk. At this point, you might be thinking, wow, partitioning. Sounds great. I have so many ideas about this. I'm going to go partition everything, couple gigs, going to partition it. Let's go. Unfortunately, Postgres has made a lot of improvements, but we're not quite there, and there's some good reasons why. Postgres partitioning also has some downsides, potential reasons why you probably shouldn't partition certain data sets, but still should for others. So you can also see a possible negative impact on performance. As I said, partitioning is not just a guaranteed win for performance. You could see worse performance on queries that don't have a partition key, for example, because imagine I'm hash partitioned, and I partitioned by ID. If I query that database without the ID, there's no logical way for Postgres to reduce the amount of partitions it has to scan from n to 1. So I'm not able to perform I'm not able to prune partitions from the plan. So now I potentially made the query worse. Also, you might see increased query planning time if you have very high partition count. This is very much reduced in modern versions of Postgres, I think like 13 plus, but before 13, when you started to get up to, I would say like maybe hundreds of partitions, you would see a very noticeable reduction or very noticeable increase in your planning time, which can add up. Now I've seen some benchmarks that say that you can do a couple thousand without any impact, so that's great, but again, only more modern versions of Postgres. Also, stronger Postgres knowledge is now required from your app developers and product. It's important to remember that partitioning takes Postgres from being kind of a black box, treated as you want it, super generic, and it kind of puts this layer of how you should query Postgres on top of it. Of course, you can break the rules, it can still do it, but it might have performance implications if you treat Postgres as a black box, continuing to kind of let app developers write whatever queries they happen to want without maybe understanding the implications. And same for you, the same as a DBA, advanced features require more advanced expertise. The Postgres partitioning system can require bespoke knowledge, observability, knowledge of gotchas, extensions. All this good stuff comes into play for you as well as people that are actually writing application code. Partitioning is worth it or recommended wherever you look online as an industry rule of thumb when you should consider it if table size is over 100 gigs. This is highly dependent on what data is in there, but this is kind of the rule of thumb you'll see. In the Postgres docs, I was actually a little surprised to see that it suggested it when table size is larger than the physical memory of the server. I haven't personally done that, so I'm curious maybe afterwards if anybody has any stories or input on how they calculate that or how that comes into play. But I have typically kind of hand-waved it around the 100 gigabyte consideration benchmark. My personal, I'd say far less official rules of thumb that are definitely not documented anywhere are range partitioning, easily the best method or return on value typically. Especially if you're especially if you always pass the partition key, of course, but also if you're frequently querying the most recent data. If your table has a natural range partition, or specifically often I see the use case if you want to expire or delete old data, this is a perfect fit. List partitioning is good if you really want to use that bulk attach, detach functionality. It really works for this. It really fits a lot of application use cases where you need to add or delete large amounts of a certain type of data semi-frequently. For example, any job where you might see, oh, I've got a cron that runs every week and it deletes like 10% of the data. That could be a good place for list partitioning. Hash partitioning is when you need partitioning for maintenance reasons. Remember, index rebuilding, auto vacuum not keeping up, You really need it to maintain that, but there's just no natural partition key. And also, like I said, hash partitioning does not support attaching and detaching, so you don't even consider that functionality. If that's something you can bypass, that could be a good answer. But I did kind of skim over something here, which was knowledge of gotchas, and this wouldn't be a good presentation unless we actually go into what they are. The biggest gotcha, in my humble opinion, is the fact that table primary keys and unique constraints must include the partition key. So if you try to create a primary key or partition on something a column that's not included in the primary key, you would see an error like this: insufficient columns in primary key constraint. So how do we get around that? You might have noticed that in my examples, I was actually being a little sneaky. So in this one, range partitioning, you can see that it's partitioned on inserted at, which is a required field. And here we can see that primary key at this point is ID and inserted at. This is able to help us get around it. It's now technically successful. However, it's not always a good idea. It's one of those trade-offs, because let's say I'm coming from a more traditional setup where students has a primary key of ID, but I want to actually partition by inserted at. If I want to change my primary key from ID to ID, inserted at, of course this now has an entire migration separate of partitioning, but also I need to be aware of upserts, because upserts need to provide all primary key fields. And also, most importantly, ID is no longer individually unique. ID is only unique for that ID inserted at combination. And so if you're migrating to this, it's very easy to potentially miss spots where you might break logic and not realize it 6 months down the line. But this is a way that you can do it. Some other rapid fire gotchas that you might consider are range and list partitioning, the default partition. Default partition, I think, is a net positive because it prevents the situation, it prevents the errors, basically prevents your mistakes as a DBA from, causing somebody to not be able to create an account, for example, or pushing it onto the application. However, I have seen situations where you create the default partition and then you say, wow, why is this, this partitioning thing really sucks. Like, why is performance so bad? Then you look and you have a default partition of 800 gigs, and then you just forgot to create the migrations or something like that. So it is something to actually keep an eye out for, and you might see, especially if you don't have observability on default partition size, you might see degradation and not realize why. Hash partitioning, you need to really be aware of range queries. So for example, if I say select where partition is between X and Y, Postgres is not able to use partition pruning effectively here. Because every value is hashed, it's not a direct hit on any given partition. It logically must scan every partition at this point. So it kind of does away with some of the benefit there. So if you're doing range, you really want to make sure that you're probably leaning towards range queries. Also, again, partition count can't be changed without completely starting this process over again. Finally, logical replication in CDC. This only applies before Postgres 13, but before PG13, logical replication was not supported. Now you're able to. You can decide if you want to publish via partition route, which basically means do your subscribers read it as one table or n tables, and that's up to you. Now on to the actual meat. We've officially gone through all the prerequisites, and now we're on to the actual point. Kind of a long lead up, but hopefully we're now prepared to get across 4 different ways of partitioning an existing table. Why is this actually a challenge? Basically, this is a challenge because Postgres doesn't support a feature like alter table students partition by whatever. This would be great, and when I've given this talk in the past, I have specifically asked people in the audience to please do this, because I think my goal is to not have nobody needed to watch this talk. But until they do so, I'll continue harping on about it. And also, it's a human problem, because when you create a table, how many people have the foresight to know they need to partition it? How many people have the foresight to know how exactly this data is going to be read and written to potentially weeks and years down the line? So in this section, these 4 examples are going to be first an offline migration, and then the last 3 being online migrations with varying levels of disk space usage, and finally the last one using logical replication. There are many ways to partition tables, and this talk I'm going to be basically technology agnostic. So I'm going to be focusing on native Postgres, not focusing on extensions. Extensions are good here. Some example extensions you can use include PGPartman, PGSlice, and PGParty, depending on what you're looking for. Of those, I have really only used PGPartman, but I've heard good things about them in different ways. So I'm going to mention them a little, and some things may be easier with extensions, but I'm kind of keeping it relatively Postgres vanilla here. Let's start off with case number 1, offline migration. So we're going to keep up with the idea of a students table. And I'm going to say that at the start of each school year, admins are going to be inserting 500,000 students for every new grad year. And they're also going to be deleting about 500,000 from whoever just graduated. I have a 100 gigabyte table, and it's serving live traffic. It's some sort of, school admin site, so it's like 90% reads, not super high writes, updates. Traffic is also very much concentrated on normal business hours, and also the school pays teachers super well, so they have no DBA budget. They just don't really want to mess with any of this. So if you boil all those constraints down, we can see that we have, maybe 3 hours acceptable downtime. They're fine with it. It's 9 to 5. And also, they have a ton of extra disk. It's a 100 gigabyte table, but they have 200 gigs of free space. And their desired schema is there on the right. They want to list partition by grad year. And if you can kind of grok that out, you'll probably figure out that it's because when they do that big insert and big delete, that we can do with attaching and detaching with list partitions. If I'm going to get started on this offline migration, meaning we're kind of stopping reads and writes during this process, the first thing we're going to do is create a new list partition table with the same schema and indexes. And I'm going to manually create the partitions for the empty table. This is very similar to what we just saw a couple slides ago. The only new thing is that you can see at the bottom there, I'm also making sure I manually create the indexes on the new SV2 table. Now, step 2 is basically do all the work. So in step 2, I'm going to manually insert the data through whatever preferred means you have. I've done the most naive version of it here, but this actually is a good example for PGPartman, which provides a function called partman.partitionDataProc, which will basically do this natively batching in a more effective way, so you're not doing one enormous insert. But the important thing is you're doing this in one transaction. I'm doing begin, basically select star from old table into new table. And then within the same transaction, before I commit, I'm going to alter the table names. So this is kind of like a little switcheroo. So users only know that they're looking at something called students. They don't know if that table is partitioned or unpartitioned under the hood. So what we can do here is we can alter the original unpartitioned table to be called students archived or whatever else you might want to call it. And then within the same transaction, rename the new shadow table to be called students and commit. Once I commit, we're back online. And even though they don't know it, applications are now pointed at the new students table, which is partitioned. Now that we're back online, separate of this transaction, I'm just going to drop the students archive table in my own time because there's no point keeping it around, because the second you finish that commit, new inserts are coming in and it will become instantly out of date. So there's no point in keeping it. That's sort of the easiest use case. And again, that was around the constraint of we have available downtime to take. But what happens if we drastically reduce that downtime from 3 hours to just maybe 3 minutes or less? So in this case, we're going to say the school district is running into issues with database maintenance time. They're doing a lot of the vacuuming and reindexing, and they also expect a lot of data growth this year, maybe 2x, 3x, so it's only going to get worse over time. They also have their read query filters, which vary significantly. There's not a lot of consistency in how people are using this data. Let's say it's a 300 gigabyte table, but you could supplant that for 1 terabyte. It could be much larger. That's just an example. And it's a little bit higher in inserts, update, deletes, like 60% read. And that doesn't even equal 100%, but we're going to say that's 40%. Update, delete, merge also, shout out, new versions of Postgres. And the traffic is pretty evenly distributed over the course of the day. So now we have a slightly harder problem. We need to do all this within a couple minutes or ideally less. In this case, we want to be hash partitioned because we don't have any query consistency. We want it for maintenance reasons. So we're going to start out quite similar to how we started before. We're creating a shadow table. Here we can use some nice syntactic sugar. we are now able to say including create table like students, including defaults, indexes, and constraints. And I'm also going to partition by ID here. Now I'm going to go through the process of creating my 10 partitions. Again, I'm deciding ahead of time this is going to have 10 partitions. Once that's done, we quickly escalate into some PLPG SQL. So at this point, I'm going to create a trigger, which is going to duplicate incoming traffic, inserts, updates, deletes. This is kind of a long trigger, so there's a bit.ly link here if you want to see the entire thing with all the examples. But basically what this says is that every time that you do an insert, update, or delete, I'm going to duplicate that traffic onto the new table. Whatever you do, I'm going to do the exact same thing on the new shadow table. So then at the end there, you see I now have to actually attach the trigger. So the trigger exists, but it's just sitting there as a function, and I'm now going to be attaching it. So after each row, we're going to execute this procedure. From the second this starts, whatever the timestamp is, data from there on is all covered. So now we know that all we need to take care of is any data before I started running this trigger for every insert, update, delete. So now you're going to run a historical backfill from the beginning of time until the time you started using the trigger. In this case, it's important that if you hit a primary key conflict, just do nothing. If you hit a primary key conflict, what that means is that since you queried that old row, it has since been updated and inserted into the new table, so you want to do nothing. There is a potential race condition here to call out. There is a potential race condition here to point out, which is that it's possible that if you are selecting data, that if you are deleting data from the new table, so let's say that I'm live deleting a profile or a student, I now run a delete on the new table, but then simultaneously, before I realize, I re-backfill it. So there's a potential race condition to avoid. One way you can avoid that is by having a second table in the background that you just insert everything you want to delete to, and then once you're back online, you can just double check they're all deleted. You can also maybe attach some heavier locks to it. I haven't personally explored that. But once that's all backfilled, the only thing you need to do to cut this over is this one transaction. Begin, switch table names, commit. And I said 3 minutes, but really this is definitely sub-second, especially if you make sure that you're setting lock timeout so you don't get stuck by anything big, then you can be really confident that this will take a very short amount of time. At this point, same as before, you're able to drop the old table when you're done. The third case is something that I will admit I have not done personally, but I read some really great blogs on, so I'm going to kind of give it a little bit of attention here. And now we're going to slightly increase the constraints. So we still have the same amount of low downtime, but now we actually don't have enough disk space to be able to fully copy this, because in both of the previous examples, if we have a 100 gigabyte table, then I need to have at least, let's say, 100 gigabytes extra. Sure, it'll probably come out to a little smaller because you're creating it fresh without any cruft or bloat, but you should always assume the worst and say 100 gigs. Here, you don't have that. You have a 300 gigabyte table, but only 100 extra gigs of space. How you can address this starts out much the same. Create your shadow table, but when you create your trigger instead, we're going to do something a little bit different, and this is a different bit.ly link. So now, instead of exactly duplicating, okay, when you insert, I insert here, update there, delete there. Instead, you're going to be doing something a little bit clever. So you create the trigger, which inserts only to the new table, deletes from both, and deletes from the old table, and when it deletes from the old table, it inserts or updates to the new table. So this all sounds a little complicated. I would recommend actually checking out the bit.ly link because it's honestly a lot to wrap your head around without visuals if you're similar to me at the very least. But what this results in is you being able to do this. So you can replace the old students table with a view. So instead of having students as a table alone, you can replace students temporarily with a view, which can union all data between two tables. What this means is that you're able to keep roughly the same amount of data over time, even though you're not able to completely duplicate all the space. So in one transaction, you can start out by renaming students to something else. And then immediately, I'm going to create a view that says create view students as select all from old and select all from new. This means that whenever you query students, because they have exactly the same schema, you just return everything from both. Then, finally, same transaction, you're creating a trigger, which in this case I called migrate partition trigger, but whatever you want. And it says, instead of insert, update, delete on students for each row, do this. So before we were saying, in addition to insert, update, delete, do this. Now we're saying, don't do that. Instead of it, do this. And again, the critical part here is that the view just unions everything from both. Once we run that live, we do the same thing. You run a backfill. How you run this backfill is up to you. I personally am actually a fan of the application side backfill here instead of a bunch of functions on the server, but maybe that's more area of comfort. When you're all done with that, you can now do something similar to the old switcheroo from before. In a transaction, you're going to drop the students view, and you're going to actually drop the function migrate to partitioned table, and you're going to alter the new table to be called students as expected. So now when you go back online, when you commit, just as before, it's now looking at a real partitioned table called students. And now we're just going to clean it all up by dropping the old table, which has already become out of date the second you commit. Nice. So now we're on to the final, most stringent requirement, and kind of a fun one, in my opinion, which is using logical replications. So we're going to start off with the requirement again. For reasons that I really couldn't make a great example for, the students table is like a terabyte or a couple of terabytes. It's just a massive school district. I don't know what to say. The district expects to regularly partition more tables as well. Maybe it has other tables just this large, and they really want this process to be repeatable. They don't want to hire a DBA for a month to make this quick and then just need to do it again next month. Also, the applications connect to a DNS name, for example, PGBouncer, but it could just be any consistent DNS rather than using the real host name. The table is serving mostly read traffic, but it has enough inserts, updates, deletes, and it's evenly distributed throughout the day. Now we're changing these constraints. We're saying I want less than 1 minute of write downtime if possible, and also we're adding a third one, which is the task must be easily repeatable. This is not a one-off. We need to make sure we can do this without potentially weeks of work to set all this up and backfill. When we do this, I'm going to go over visually first, and then I'll show a list in case that's more how you intake it. We're starting off with a situation like this. Right now, I have a lot of application backends that are pointing towards a connection pooler or just a static name, and that's sending reads and writes to this server that has our students table on it. I'm going to set up a second server, a totally different server, not a new table on the same server, but a new server, and I'm going to set up this identical table with the new partition schema. Again, schema same, but now partitioned. I'm still sending all reads and writes to the original one. Now I'm going to set up a logical replication slot from the source to the destination. So I'm setting up a publication, and then I'm creating a replication slot from the destination, which is going to be basically catching up from the beginning of time and rewriting all of that data as a subscriber into the downstream. If you're not very familiar with logical replication, I'd recommend that if you do this, you definitely kind of do this in other circumstances first. But this is nice because you don't need to do any backfill. It will both historically backfill as well as keep up to date with any new updates, inserts, deletes, good fun stuff like that. Now I'm going to switch over just the reads. So this is, 0 read downtime for here. If I'm lucky, I have like a read-only user in Postgres that is easy to just point to a new host. If I'm unlucky, maybe not. But this is what you can do if you do, so maybe consider that. The next thing you do, and this is where you start taking downtime, is that you cut off writes to the original source. Once you cut off writes to the original source, what you basically need to do is just wait until the most recent last write on the source is written to the destination. You can do that by running a query similar to this, which will just tell you how far wall is behind on the source versus the destination. I personally also, if I'm doing this manually, like to idiot check and just select the most recent there and select the most recent there, but that's just me. Once you're sure that it's totally caught up, all you do is that you switch the hosts on the connection pooler level to point writes to the destination as well. So notice in none of this have applications changed anything. All they know is, oh, I can't reach the database for some reason. They don't know why. All you know is that you're changing the hosts on the middleware level, essentially. if you write all this down, and I mostly keep this in here so that when I upload slides, people know what I'm talking about, it looks like this. Some other details are, of course, ensuring that you have a primary key, making sure that you're creating the publication with partition published via partition root is true, because that makes sure that you're publishing as one table, not as n tables. Also making sure that while logical replication is running, you don't do any migrations. There's no DDL changes. So, because if you create a new column or a new index, that will not be carried over during that process. Secondarily, sequences are not copied over in logical replication. So ideally, you don't use sequences. Maybe you generate them on the app side. But if you do, you'll need to take additional downtime during cutover to copy them all over to the destination manually. And then all the rest of it, I pretty much already said. So if you want to see the slides, they're available online. You might also have noticed I said a new fresh database instance. Is that totally necessary? Because it seems like it could be quite convenient if you could just logically replicate students to another table on the same instance. Then you don't need to set up the extra hardware and it gets a little less complicated. But that's not quite true. So schema, table, and column names must be the same on the publisher and the subscriber. You can use one server, however, the database would need to be different. So you would need to be publishing from a database on the source to a different database on the same source, which, you know, you can. I don't know if I'd personally do it, but you can do it. However, I would say this also provides the opportunity for essentially a free upgrade. So you can set up the downstream, for example, as like Postgres 16, and then you get a free upgrade and other nice things out of that, instead of just, you know, doing all the work and not getting a Postgres upgrade out of it. Now we've kind of gone through all these steps, and we're finally on our new partitioned table. Everybody already celebrates, everybody's having a great time, but now we actually have to maintain it and make sure that it stays in good health. Some things to consider are, first of all, maintenance, regular creation of new partitions. With everything but hash, you'll probably need to create a new partition now and again, or at least potentially. PGPartman is most common for either of these. That's what I've used. But it is a way to automate the creation of new tables as well as providing other functionality under the hood. You can also use it to create or delete or detach old partitions on a schedule. And it will allow you to run some SQL like call partman run maintenance proc to do this effectively. Observability is also important. Monitoring and alerting is something that you might need to do differently in partition tables. For example, you will want to monitor that your partitions are created and deleted by PGPartman and the cadence is expected. So you want to alert both on, your cron job, which creates them running successfully, but also alerting with lack of data. In case it fails silently, you don't want to be surprised if it doesn't pre-create the set number of weeks which you set up. Also, I recommend monitoring for partition size skew. So you can expect skew on list partitioning and sometimes range partitioning as well, depending on your actual data set. But you might be able to monitor on the number of rows in the default partition, for example, or the disk size of default partition is a good thing, so you don't run into that foot gun that I mentioned where suddenly you have a massive default partition. Now you have to deal with that. I would also recommend setting up Postgres auto-explain. I recommend this in general, just a general recommendation, not a partitioning specific one. But here it can be extra helpful because you might see dynamic changes in your query plans as queries are introduced that don't use the partition key. And auto-explain can help you identify those more proactively. Like I said, with partitioning, you're now providing no longer a black box for developers. There's kind of a right way and a wrong way to potentially query a table. And so putting more of these tools into their hands can be helpful so that you don't have to do all that work yourself. And finally, configuration. Configuration changes that are made on the basis of table count might need to change. Like I said, Postgres considers partitions just regular tables. But if you grow from 1 to maybe hundreds of partitions, there's configs that might need to change. One, for example, is auto vacuum max workers, which defaults to 3. You might want to consider increasing this so you can parallelize your auto vacuum. Of course, the further you increase this, the fewer those workers are available to service queries. So it is a trade-off, but you might want to consider it and just see what you're running at once you partition, and then maybe increase if you see you're always maxed out. Finally, organizational support. Beyond the tech stuff, how are you actually going to be making sure you can support developers and yourself to maintain years of partition tables down the line? Some things that I'd recommend would be writing internal or open source blog posts about your experience. One thing that we've done at Brex is we have used a Git hook to link documentation when people do schema migrations. You could automatically link migration information if people try to introduce queries that don't use the PK, for example. Especially if you don't use an ORM, that can be quite doable. TLDR, I would say think about how can your partition table stay performant and well understood going forward, and how can you enable engineers to write queries what you're considering the right way. That's all for me. Thank you guys so much. Any questions? Yeah?
I wonder if you happen to know, does partitioning handle duplicate records the same way a SEAPUG table would? So if you have a constraint, but then inserted at, let's say it's like a range partition, so inserted after it's like updated, but there's a duplicate record from like the previous partition.
So the question was, does Postgres handle, does it handle unique, like potentially duplicate rows the same way as other systems? And I would say Postgres doesn't do anything special for that. However, one of the main gotchas is the fact that your partition key must be included in the primary key. So one of the reasons it actually enforces this is to be able to enforce uniqueness constraints across partition tables. So in the case that you have a range partition table, and you have a partition key, if inserted at, or let's say it's like ID comma inserted at is your primary key, and you're partitioning by inserted at. If you insert values that for different IDs, let's say student IDs, and then updated that or inserted that, the uniqueness constraint will be upheld, because whenever you try to insert it, it will still provide the uniqueness check. It's just able to leverage basically the primary key index to do it within a reasonable amount of time. So you don't really have to worry about like duplicate data any more than you would a regular table. It upholds it essentially the same. Does that make sense? Yeah?
For logical replication, you said you get upgrades for free. Do you have to drop your extensions in the original database?
So the question was, I said that logical replication, you get upgrades for free, and does that mean that you have to like recreate extensions? And yes, that's not something that I've personally dealt with, because in the way that we set up new servers, we kind of pre-package with all the extensions we use, so I haven't had to do it very manually. But you would have to. Like, so for example, if you're upgrading in place, one of the steps you have to do is like reinstall or upgrade all of your extensions as one of those steps. So if you're setting up a new server, you would install the new version of Postgres, and you would need to manually ensure that your extensions are all up to date. So you would need to redo that manually. Yeah?
What happens if you have a row which has, let's say it's partitioned by insert path, update the insert path such that it now should belong to a different partition?
Yeah. So the question is, what happens if you update the value in a partition key? And the answer is that it moves it to the new partition. So if you are partitioning by inserted at, or let's say updated at, that's a better one. If you're range partitioning by updated at, and then you update a row, then it actually, it will use MVCC, so it'll update X max of the old tuple, making it invisible until vacuum comes by on the older partition, and it will actually like reinsert it into the new partition. So it's like physically located in the correct partition. Yeah?
Is there a reason to use list partitioning instead of just a range partitioning, a very small list of values, or a very small range?
Yeah. So the question was, is there a reason to use list partitioning versus range?
Yeah, we just have a very small range.
Oh, I see. So like range of essentially 1?
Sure.
I mean, at that point, it's the same So I don't think there's any real differences there. I think it just depends on how dynamic you want it to be. I don't think, as far as I know, there's any like Postgres specific differences between those two. You know, if the logic behind how you put a tuple in a certain place is the same, I think it's all the same from Postgres' perspective, but I actually hadn't thought about that before.
If you want to partition by an email, I think the syntax would be a lot less cumbersome.
Yeah, that's actually a good thought. I do internally sort of think of list partitioning like an enum. You know, if you have to add one now and then, not a big deal, but it's not something that you want to be doing constantly. Any other questions?
How do you do with schema migrations with partitions? So with student schema and this partitioning, let's say I want to run GPU.
Yeah.
Postgres transparently do that.
Yeah, that's a great question, and honestly something I should add to the presentation, which is, so the question was, what happens when you need to do migrations once you're already partitioned? So migrations performed on the parent table, in this case students, will be automatically applied to all the partitions. So if I add a column, it'll add all the columns to every partition. If I add an index, it will create an index in every partition. So it will all be copied over. It is important to remember that some of these migrations could lock those child tables the same as it would lock a regular table. So, you know, if I, for example, I'm partitioning in Postgres 10, you know, Postgres 10 still locks the whole table if you create a column. So in that case, it would do that with all the children tables at once parallelized.
That was going to be a follow-up question. So it is parallelized, right? So every index is parallelized to the index region.
Index, yes, but the constraint is actually how many maintenance workers it has. So like if you have enough maintenance workers, then it'll parallelize it like up to that. But there is some point at which it would need to do it essentially in batches. Any other questions?
In the beginning, I liked how you differentiated sharding from partitioning. In sharding, I usually work a lot with like NoSQL databases or scaling. There's usually a concern of like a hot shard, so you want to try to avoid that. In partitions, it seems like there's no such concern. Like this, you're still sharing the same resources, so it doesn't matter like if most of the requests get fulfilled from a given partition, or is there a similar concern of like hot partition?
The question was, do you run into the problem you run into with sharding, where you might have like a hot or like a really popular certain shard that, you know, everything else is basically doing nothing, but this one shard is experiencing kind of a ton of work. And you can still experience that because how active your partitions are completely from the application. So with the exception of hash. With hash, you can't run into it because it's just naturally distributed. So logically, you wouldn't run into hot partitions. But with range or list, I would say it's actually quite expected that you would have certain partitions that are essentially servicing more traffic than others. With range, for example, it's really common to use it for the use case where, let's say you have an expenses table, and you're usually querying for the last couple of days, and only now and again do you look historically. So your most recent partition of maybe this week is going to be a hot partition. However, in Postgres, that's like not usually such a bad thing as long as you're not doing lots of locks. It's just like a normal Postgres table. If you're doing locks, you know, generally readers don't block writers and writers don't block readers, but if you block each other, that can have downstream implications. But if you're reading a lot from it, it will just have more space and shared buffers. And so you'd ideally be reading more from cache. So it's not as bad. I would say that in some cases, it's even kind of good for it to be a hot area because it means you're throwing more of it into memory. And so your popular areas of the data set are going to be more in memory and faster. Any other questions? Yeah.
Just generally, why would you need to necessarily, obviously it's good to have smaller databases just for maintenance.
Yeah.
Why would you need to stay away from like a terabyte of data?
Good question.
Like why did you pick 100 gigabytes?
Yeah, so the question is why 100 gigabytes and why are large tables potentially hard to manage or bad for outcomes? So the first reason for 100 gigabytes is that it's just a rule of thumb. I think there's plenty of times when you don't need to do it for hundreds of gigabytes further. And I haven't yet seen one where you actually need to partition smaller than that. Possible, Maybe you have. Okay, that's good to know. I haven't. But, that is a rule of thumb. I would say you consider it at 100 gigs. Like, you consider where the data growth is going. But a lot of the reason why you want to consider partitioning is really the maintenance side, because the maintenance is not just, it takes me a while, I have to keep a screen open while I create this index. It can also have long-term effects on your table health and how healthy your queries are going forward. So,
Like re-indexing would take
yeah.
days.
Yeah, so for a more specific example of that is like if reindexing is taking days or if vacuum is taking days, then it's actually holding X-min horizon during that period, which means that you're actually building up a lot of table bloat, which means you're actually using way more disk than you need to, and your queries are going to start taking a lot of I/O. So they're going to be slow and expensive, neither of which we want. So I would say that the maintenance side is like a personal convenience, but it also has really long-term health reasons for the database itself. I would also say specifically databases being terabytes is totally fine. It's more the table level to be concerned of. So databases, I'm sure there's some size where you don't want to go over. I haven't run into it. But on a table size, is where you start to run into those maintenance concerns that lead to user experience degradation. And that's where you're going to start hitting it. Look at 100 gigs, but realistically it might be a little higher depending on your application. But there's nothing like objectively wrong with it. It's just it might not serve you well. Yeah?
If you deal with that, create a new partitions as a part of the maintenance, is that a good idea to pre-create more partitions than what you need?
Yeah, I think so. So the question is, if you're regularly creating new partitions, is it a good idea to pre-create more than you actually need? I say definitely yes. It gives you a buffer to basically make mistakes and realize your mistake and then fix it. With PGPartman, actually, it lets you auto-configure how many partitions you want to make ahead of what you need. So, for example, when I set up, I partitioned a data set, I think this summer, and it was a weekly range partition, and I set it up so it pre-creates 4 weeks worth of partitions. And there's no downside to that. It's just an empty table. So it's not a bad thing. If you want to, you can also just pre-create years and years of them, and all it is just sort of like, it's okay. I do slightly take that back. It's not a great thing because if you get going lots and lots of partitions, then the database still needs to consider it in the query plan. So that would eventually be a downstream negative effect from having tons of pre-creates, but having at least like 4 to 6 is just a good idea. And using PGPartman to schedule that and configure how many you want pre-created. Any other questions?
Yeah, I had a question kind of related to that too. So you mentioned partitions are great, but don't go crazy with them.
Yeah.
Don't
Yeah.
create too many. So how, I assume that there's going to be some trial and error at some point. Once you want to experiment and maybe benchmark what is the proper partition number for your data set, how would you go about it? Is there an easy way with PGPartman, for example, to do that?
So the question is, how do you figure out how many partitions to have for a data set? So I guess a quick definition is, before I was talking about how many to pre-create, like how many towards the future. In that case, I would personally say, like, have enough for a couple weeks of mistake time. Have whatever, if your partition is daily, that might mean, 21 extra partitions. If your partition is weekly, maybe it's just 4. But I would just add in enough buffer that you can go on vacation and realize it when you come back. If you're asking about how to decide your actual partition count, that is not, unfortunately, it's not an exact science. And it's honestly very challenging to do. In modern versions of Postgres, I wouldn't stray too far away from like hundreds is probably fine. Less than that is better. But thousands is probably too many. And this is just like personal rule of thumb for me. I generally try to keep on the fewer side, because you start having query plans. The more partitions you have, the more important it is to pass the partition key always. Because if you have thousands or hundreds of partitions, if you're not able to do partition pruning, so basically to narrow it down to just 1 or just 3, then you're going to need to do a lot of parallelization. And if you have a lot of workers going, you might not be able to parallelize all that at once. So it's really kind of like a risk analysis, I would say, of how bad is it if I have to scan them all at once. Is there one more question over there? Cool. Anything else? One more question.
After your partition are created, I'm assuming you can delete any partition. You insert a new partition in the middle.
Okay, so do you mean an arrange partition?
Yes.
So-
Our range is not, say, for the list.
Okay. So the question was, if you have a list partition, let's use our example of regions. I know I can drop a partition, but can I put it back? Is that the question?
No, you can drop. Okay, drop is the 2 seconds. You can drop a partition from the end or beginning. Now, can you drop a partition in the middle?
Yeah. So in a list yeah, sorry.
That's one thing.
Yeah.
How about the insert? Now, if I have a need to insert a new partition in the middle of the table,
So Postgres doesn't have, so the only partition type that has a concept of ordering of partitions is range. So in lists, if we had regions, there's no concept of like the middle partition. So if I had regions, let's say like 50 states, 50 US states, Postgres' organization of where those partitions go is completely up to Postgres. Like there's no human decision making of order. The only partition option that has a concept of order where you could like potentially insert between two partitions would be range. And my answer to that is I don't know. Because I personally haven't, for example, needed to, let's say I have a range, 1 to 10, 11 to 20, et cetera, et cetera. I have not personally dropped, let's say 11 to 20, and then, or tried to change it so that you have, from 15 to 25. I haven't done that. I think it would be possible, but you would basically need to you would basically need to start from the beginning, I think, because you would need to migrate data in tuples within partitions themselves. So you would either need to take downtime or just start over and create a new table. But I haven't personally needed to do that. Last question? What features is Postgres missing? The number one that I already kind of give a shout out to is just alter table partition concurrently. That is like that's on my wish list pretty hard because that would just be super convenient. Not gonna lie. Then this whole talk wouldn't exist. But other partitioning features that would be helpful. I think if we were, one of the gotchas I mentioned was the fact that hash partitioning can't do range queries. If it were possible to kind of track that, that would be nice. If you could do, if you could do partition pruning so you don't have to query every partition if you need to do a range within any data in hash, that would be good. I don't think so. I think a lot of the maintenance stuff is taken care of by extensions, and I think I like Postgres' policy on keeping core pretty basic and allowing room for development of extensions. So I don't think there's like a reason that what is in PGPartman should be in core, for example. But yeah, the biggest one would just be those two.
Global unique indexes are the other big one.
Oh yeah, global unique index. Oh yeah, the other one. I would say that's a very good call out. I wish that I did not have to include my partition key in the primary key. I wish that migration didn't need to happen. That's a very good call out. Thank you.
I was going to throw one more thing out too.